Hi, welcome to our first video. So we're going to talk about parent functions, graphs, and transformations today. Now, the parent functions, it's really just kind of that shape, and then we'll talk about what are the different transformations that happen to those parent graphs. And then we're also going to kind of go into the idea of what are the domain and range of the various parent functions. So the first thing we want to address is what is a function versus a relation, or what is a relation versus a function. So a relation is kind of the relationship between sets of information. And so what we kind of consider those is that it's a set of ordered pairs. So it's the relationship between any x values and y values. So a relation is any set of ordered pairs. Now you want to consider the fact that a relation can have various ordered pairs. So you can have 0, 1. You could have 1, 1. You could have 2, 1. You could have various things that all give you y equals 1. And so when you have various x values equaling the same y value, it doesn't make sense as a function because it's not what we call one-to-one. And so we consider it a relation because it's a relationship between sets of information. So a function is the difference is a function has one y for every x. So the idea behind this is that you have one y value for every one x value. And the other thing you can consider is that if you remember the vertical line test, this passes the vertical line test. So that means you can take a vertical line and pass it from left to right over the graph. And if the vertical line is only ever hitting one point as you pass it, it passes the vertical line test. So let's talk about what the domain and range are in terms of functions and in terms of the coordinate plane. So the domain is the set of x values. So we say it's all x values. And then for the range, it's the set of y values, or all y values. Cool. Now let's talk about what are different parent functions. So when we have different parent functions, let's start with the most basic. We have a linear function. So linear function, the characteristics of it is it's a line. It's a straight line extending from one direction to the other. And some things to note about this is that the domain and range are usually all real numbers. So the way that we write that in interval notation, which means it kind of looks like a coordinate, is you have negative infinity to positive infinity. You could also say that it's the set of real numbers, in which case you would say the domain is the set of all real numbers. So it's that fancy R. And you could also say the range is the set of all real numbers. Now, what would I prefer and what would AP prefer? Interval notation, always. So let's talk about quadratic functions. Now, when we're talking about quadratic functions, it's kind of the next power of our linear functions. And so what it does is instead of a line, it curves it. And so things that you want to really remember here is that these are sets of positive x values. It's always going to be positive because it's going off of the square. And so if x is a positive or x is a negative, it's giving us positive y values. So how does that adjust the domain and range? Well, the domain can really be negative infinity to positive infinity, but the range is only ever going to be positive. So it's going to be 0 to positive infinity. Now, if you notice, I had a soft bracket around 0 here. And for those of you wondering, Miss McNinch, this intersects that 0. Shouldn't it be a hard bracket? Yes, it could be a hard bracket, and that would be proper notation if you wanted to include that. I, however, am specifically not including it because College Board actually does not mind if you use a soft or a hard bracket, because they care more about the numbers of the interval than they do the correct bracket. So if you worry about brackets all the time, you can sigh relief, because this is going to be so much nicer. Now, this is going to be a hard bracket, which means that 0 is included. Soft bracket means it's not included, so it does not pass that value. Now, what about the soft brackets around infinity? Infinity is not an exact value. It's not a specific point on the graph. So you can never, ever, ever have a hard bracket around infinity. Now, moving right along, we have a cubic. So we're adding another power. So when we have a cubic, what actually happens is we end up getting negative y values, because we would have, if x is a negative value, that's a negative times a negative, which is a positive, times another negative, which is another negative. So how is that going to change things for us in terms of the domain and range? Well, it's actually going to make things a lot simpler, in that the domain and range is going to go back to negative infinity and positive infinity. The range, oops, I said that backwards. The domain is staying the same. The range is going to go back to negative infinity and positive infinity, similar to what it was in the linear function. Now, when you have a cubic, it does kind of have this curve to it. And I remind students that this kind of looks like a John Travolta or a disco. So I always say that this is the disco graph. Now, the absolute value function. So let's talk about the absolute value. The absolute value is the positive value, or the distance away from 0. So it's a measurement on a number line. So when we're thinking about it, it's how far away is my value from 0. So it's only ever going to be a positive value, because we're talking about the distance away on a number line. So it has these two brackets that go around it, those two lines. That's what is the characteristic function notation for an absolute value. And so what is the characteristic shape of an absolute value? A V. So that V is a hard point right there at 0. It is not a curve. And the reason why it's not a curve is because it's always going to be a linear function going one way and a linear function going another way. We'll talk about that more, because that's an assignment I have for you. So some important tips to remember is that even though this is kind of a little bit pointier than our x squared, our quadratic, it does have the same domain and range. So the domain is still negative infinity to positive infinity. Any x values go, but the range is specifically only those positive y values. Now again, keep in mind this is the parent function, and so that parent function is going to just give us that shape without any transformation. So the range might adjust depending on what transformation is happening in the absolute value. The range, or the domain, could it just? We don't know. You'll have to find out. So what about square root and radical functions? So for square root and radical functions, those really just stay in this positive area, because you really can only have positive x values in a square root, and positive square roots are only going to give you positive y values. So you want to think, what is the domain here? And that's only ever going to be positive x values, so 0 to infinity. The range, same thing. It's only ever going to be positive y values. Coolio. Now, what about a rational function? So a rational function is what happens when you have an x in the denominator. So what happens then is you have something interesting at 0, because if this x value is in the denominator, what happens when you have 0 in the denominator? Everything explodes and the world as we know it crumbles. So we really don't like to put 0 in the denominator. And so what ends up happening here is, so I have it kind of as two separate ones. So when we have f of x equals 1 over x, it's this black graph here. And it's what I kind of refer to, it almost looks like a butterfly in my mind. And then when you have 1 over x squared, how does that change it? Well, it means that you can only ever have positive y values because you have an x squared in that denominator and you have a positive 1 in your numerator. And so that's only ever giving you positive y values. So let's talk about how is the domain and range going to be written for this rational function. So as I said, it can't pass over x equals 0 because we don't want a 0 in the denominator ever. So we have that the domain is going to be from negative infinity to 0. And we are going to put a soft bracket because it does not intersect 0. Then we're going to do a U because it stands for union. So you have a union between two intervals that kind of tells you, okay, it goes from negative infinity to 0, and then it stops, and then it jumps, and the interval starts from 0 to positive infinity. So what is it jumping over? It's jumping over that y-axis essentially, because that's x equals 0. Now, how does it change with the range? Well, very similarly with that range is, okay, well, it goes from negative infinity to 0, it looks like, and oh, hey, it's also going to jump over that y equals 0 and 0 to positive infinity. Now let's talk about the 1 over x squared. So I'm going to write those in red so you can kind of distinguish them in the notes. So the domain, well, what changed here? Well, we can actually go from negative infinity to 0, and it does appear that we do kind of bounce over that x equals 0 part. So we still have the same domain, it looks like. But what happens to that range? Well, that range actually only stays in the upper half of the graph. So it only stays positive. So our range is actually going to be anywhere from 0 to positive infinity. And so you're probably wondering, well, is there a union between those two pieces of the graph? No, because it's just that upper half, okay? So we didn't have to cross over a y equals 0 here, so that's union that we used before is irrelevant. Okay, now let's go into our natural exponent. So the natural exponent is the e to the x. So the e to the x, you're wanting to memorize this because it comes up so much. So some things that I have students write down is, I have you guys write down this graph, the graph and the table is what I meant. So when x is equal to 0, you have e to the 0, which is 1. Why is that something I want you to put down? Because that is an easy point to remember. So you go ahead and put that first point down. The second thing you're going to do is, what's when x is 1? Well, when x is 1, that's just going to give us the value of e. E is approximately 2.72. So I tell people, go to about 2.5 and go up just a little. Again, we're really going for the shape of the graph in terms of this parent function as opposed to the actual accuracy of the points. If you're looking at accuracy of the points, you will have a graphing calculator available. You're not going to have to graph complicated things by hand and have to determine values like that. AP is not mean like that. So if you can remember these values and this table, you will be able to recreate that e to the x graph every time. Now, the domain and range here, let's talk about that domain and range. So when you're talking about these x values, you have that the domain is, well, it looks like it's going from negative infinity to positive infinity. It goes all the way across that x-axis. Well, what about that range? Well, this is only in the upper half of the coordinate plane. Ugh, I'm mumbling over my words. So this is going to be from 0 to positive infinity. Okay. Now, after you have the natural exponent, you can kind of go into the natural log. So the natural log is that ln. of x. So that ln of x, I also have you guys memorize a table to make this a lot easier. So the table that you want to memorize here is when x is 1 and when x is e. You also want to memorize what are those natural log values. That's going to be super helpful when you're doing calculations later on. So when x is 1, the natural log of 1 is 0. When x is e, the natural log of e is 1. Well, what happens when x is 0? Well, let's look at that domain. It never crosses over, and so it never gets to x equals 0. So it would be a soft bracket, 0 to positive infinity. Now, what about the range? Well, even though it is kind of slow moving, it is going to go from negative infinity to positive infinity here. Okay, cool. All right, let's get into those trig functions. So we're going to have you, and by we, I mean the royal we. Sine and cosine functions are really the ones that you want to know the graphs of. That's going to be super helpful because personally, I prefer looking at the sine and cosine graph in order to calculate for radian measures or calculating for 30, 60, 90 triangles. So the reason why I kind of remember the graphs as opposed to the right triangles in the unit circle is because these become a lot more useful and you can learn a lot more about the functions when you're looking at a graph. Also, calculus you will learn is very visual. So let's look at these trig functions. So for the sine of x, you have the following setup with pi over 2, pi, 3 pi over 2, 2 pi. Those are the 4 x values you want to include. You have -1 and +1. Those are your y values. This, again, is a parent function. So it's just the basic. So you really are kind of going from 0, 0. Pi over 2, that's going to be 1. Well, what's pi? Pi is going to be 0. Well, what about 3 pi over 2? That's going to be -1. Well, what about 2 pi? That's going to be 0. So when you are looking at the domain and range of this actually is a little bit interesting because when you're looking at these trig functions, they have something a little different, and that's called the period of it. So these come in periods of from 0 to 2 pi, and then it repeats this same exact pattern. So the domain is going to be from negative infinity to positive infinity. As you can see, it can go on forever in both x directions. Well, what about the range? Well, this is really only ever going to ping and pong between -1 and 1. So our range here, I'm actually going to use my hard brackets, -1 to +1 here, and that's our range. Well, what about cosine? So this one is similar in the domain and range in that the domain and range are exactly the same. So when you think about the cosine graph, what's different about it is the values you have for those 4 x values. So when you have pi over 2, that's 0. And then you have pi is -1. 3 pi over 2 is 0. 2 pi is 1. And so this kind of, it follows a different route. And so you do want to make sure that you remember what are these 4 x values giving us in terms of y. Now, what is the domain and range? Domain is -infinity to positive infinity. Range, same exact thing. -1 to +1. Okay, now let's talk about the transformations that happen. So these are all the parent graphs that you need to know. Now let's talk about the types of transformations that can happen with the various parent graphs. So the parent function transformations are the ways that we can change our functions. Will show up in a variety of these ways, or one or multiple. It'll kind of mix and match between them. Okay, so the first one we have y is equal to negative f of x. So when we have y is equal to negative f of x, that actually is going to reflect our function And that's going to actually reflect it over the x-axis. Now, what happens when we have y equals f of negative x? This is going to reflect it over the y-axis. So another way you can think about this is that when this negative is here, you've made the function negative, therefore you've made all those y values negative. And so when you make the y values negative, that's all the stuff that's kind of, negative goes top to bottom. So when you flip from top to bottom, you're flipping over that x-axis. Well, what about when you have that negative with the x? Well, that means you're changing all of the signs of your x's. So you're moving left and right. So when you're moving left and right, then you flip over the y-axis because you're moving left to right. So think about what are these actually doing in terms of the graph and how are they changing the motions. So what happens when you add or subtract a value from the function? So when you add or subtract it, it's going to shift it up or down d units. Now what happens when you have that a different value, say c, and it's being added specifically to that x? Well, again, that's going to shift it left or right, depending on the value. Okay. Now, the language of the next ones is a little interesting. So the value a is actually going to kind of change the function in that it's going to increase those y values by a specific number. So that can go in one of two ways. So it's either going to create this thinner type of function, or it's also determined to be steeper. So I say it goes skinny or steeper. And so if you think about, okay, if this is going skinny or steeper, then the other way would go wider and flatter. Okay, now the next two specifically have to deal with what if you have an absolute value over the function versus over the specific x? Well, when it's over the function, this means it's all positive. So you only have positive y values. You only have positive outputs. Now, what happens when that absolute value is around the x? Then it means you have everything, so you have no negative x. In other words, it eliminates the left half of the x-axis. Okay, so you have a couple of examples that I'd like for you to try on your own. I do have one of them solved for you. And so go ahead, pause the video and try these on your own, and then I'll go over them with you in a moment. All right, so that first try that you had was 3x squared plus 1. So hopefully you recognize that plus 1 was going to shift it up, and then that 3 was actually going to make it thinner. Now, if you saw that absolute value of 2x, that's going to double all those x values. And so again, that's going to make it a little thinner. Now, when we're looking at the next one with sine of x over 2, so you can also actually read this as 1/2 sine of x. That might be an easier way to see how this transformation works. Because what happens is instead of going from -1 to positive 1, it goes from -1/2 and 1/2. So it actually kind of shrinks that range a bit. Now, what about this last one? So you had x cubed over 3 minus 4. So that minus 4, hopefully you recognize, is going to shift it down 4. And then that divided by 3, that's going to actually stretch it out a bit, right? So it's going to create kind of a little bit of a wider graph, wider disco. So I hope this was a great first video, and you guys can go ahead and get started on your homework. I will see you in the next video. All right, bye.